All right. All right. So, yeah. All right. So we were discussing partition in case of the hive. Okay. So if I remember correctly, so this is where we were. Okay. All right. So our last, not this one, not this one. We actually talked about HBase. In HBase, we talked about, we did hands-on and all right. So we did hands-on on. I think, yeah. All right, great. So we need to start today. So just help me understand. Am I missing something here? So from 7 o'clock we had talk. Okay, so did we talk about Bloom filter by any chance, Harita? Oh, right. You're right. Thank you. Yes, great, great. So yes, all right. This needs to be realigned. All right. That's what happens when you take a break. Okay. All right. All right. So we had actually talked about Zookeeper as well, as I can see here. All right. So, okay. So we have already talked about Zookeeper. Do you have any questions on Zookeeper? Yeah, we were here when we finished the last session. Okay. So there are some questions. Okay. All right. All right. Great. Great. So, Rohit, regarding the MapReduce question, can we have an offline discussion? Okay. And we can record it and then put it somewhere as a general one. All right, all right. So we are through with the. Okay. So any questions with respect to the zookeeper? No questions. All right. So when you have a big need of coordination, when you have a big need of coordination between various entities, okay, coordination could be discovering a service, loading certain configuration, and making sure that two services in the network do not stamp on each other's feet. So, so basically, making sure that two services stay healthy and they work in conjunction in the network. So, in those cases, Zookeeper is very good, and it helps us solving the problem of big data by solving the problem of coordination between various services which are churning big data. All right. So that's what we had discussed, and we also talked about the various features of Zookeeper, and we also talked about how HBase uses Zookeeper and other services are using Zookeeper. All right. Any questions at this point of time, everyone? Any questions with respect to Zookeeper for me? Dilsad, Harita, Pankaj, Peter, Shashi, Xiao. No questions? All right. All right. So today I want to start the discussion with something very interesting. Okay. So instead of jumping into Scoop Flume, I would like to skip session number 9. I'll go directly with the Spark. All right. Okay. So I want to utilize this initial freshness with the okay for the whole session. All right, so here we are, and all right, there's some candidate who is not able to join. Just give me a second. Hello. All right. Hi, Srini. Hi, Srinivas. Are you able to hear me? I think he's joining now. All right. Sorry for a little disturbance. And actually, this my emails are for some reason going to spam folder. Okay, and I'm not able to figure out why is it happening that way. Okay. Hello, Srinivas. Are you able to hear me? All right. All right. So I hope everybody is able to hear me. Great. Great. So now starting with our very interesting discussion on Apache Spark. Okay. All right. All right. So we had discussed Zookeeper, and we are about to skip the session number 9, which is Scoop Flume Uzi Mahat, and we are starting with the Spark discussion. All right. Should we start? Good. Good. All right. This one was on 22. All right. All right. So is everybody able to hear me clearly? So now we are going to discuss something called Spark. So what exactly is Spark and why do we need it? Along with that, we will do a hands-on on Spark so that you have a very clear picture as in what are the benefits of using Spark. All right. So actually, I'm not seeing your response, so I'm a little worried. Great, great. So, all right. So far, we have used all the tools which have been staged around Hadoop's MapReduce. For example, Hive was converting all the queries into MapReduce. Pig was converting all the queries to MapReduce. Same was the case with um, other tools such as HBase. If you try to run MapReduce on HBase, it uses the underlying MapReduce. So effectively, all of the tools were using MapReduce. All right. Now there were some problems with MapReduce which we must have realized by now. Every query has certain boot up time. It takes some time to start. Similarly, everything with whatever as part of MapReduce, the input of MapReduce comes from HDFS, goes back to HDFS, right? Therefore, if you do not want that kind of long, So when you write something into HDFS or read something from HDFS, first, you might be reading from the network. Second, you might be reading from the disk. Therefore, disk as in HDFS indirectly reads you from the data node. So every time you do some computation, there is always a problem of reading from the disk and writing to the disk, or reading from the HDFS and writing to HDFS. Correct? And that's what causes a latency. If we are only talking about minor transformation, so we end up with lot of reads and writes in the disk. Okay. Okay. So what if we could utilize m- the whole network's memory in order to solve our not so big data problems? Okay. And that's where the Spark comes in. Spark is a really fast map reduce, and it is around, as per their claims, it's around 100 times faster than MapReduce in memory, and 10 times faster on the disk. It builds on the similar paradigm like MapReduce and is integrated with Hadoop. All right. Now, the most important part about Spark is that it can, can interact with almost every kind of service and the data store. All right. So as you can see in this diagram, Spark also runs on top of the 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 yarn. Okay. So whatever Spark we would be running on top of yarn, just like MapReduce. Okay. So you can see here in this diagram. So the first thing we uh, need to understand it, just like MapReduce, Spark also runs on top of Hadoop yarn. Okay. Now, the interesting part is that you can run Spark on Amazon EC2 as well directly instead of running over yarn. And it can also run as a standalone, and it can run on something called Mesos. Mesos is a resource manager just like Yarn. What does Yarn do? Yarn runs our program in the network. We create a program which can talk to Yarn and get its parts executed in the network. Just like MapReduce gets maps and reduces executed in the network. Okay, so MapReduce tool or product, or you can say the library, it talks to Yarn and tells that run map here, run reduce here. Once maps is done, then hand over to reduce and so on. So those kind of things are done through Yarn. So Yarn you can think of like some kind of an operating system to which you can give your program and ask it to execute in certain fashion. All right. So it was running MapReduce of our usual MapReduce, right? Similarly, it was running HBase also. For that matter, the long-running processes like HBase, they are also run inside Yarn. All right. So it's basically a resource manager. It doesn't care what does your program do inside, as long as it is within the boundary of what could be done on each node. All right. So Yarn is something like a distributed operating system where we run something in the network. All right. So uh, on top of Yarn, we run many services as we have already discussed, and similar is the case with Spark. So as you can see that you can run Spark either on Yarn, okay, which is the classic way of running it, or Amazon EC2, or standalone. Standalone means you install Spark on say 100 nodes, or say multiple nodes, and then we inform each node about other nodes. And then when we start all of these nodes, they start collaborating with each other. All right, they start collaborating with each other and start running. That is standalone. And similar to Yarn, we have Mesos. So on top of these kind of resource managers, Spark can run happily. Okay. Now, first is, what can Spark do? That is the first thing. And how can you interact with the Spark? There are two aspects to it. One is, what all things does it provide to you? Okay. One is, so what all things does it provide to you? At the most basic level, it lets you do some kind of a map reduce in the network. That's the most basic level. Second is, it it can interact or read the data from all kinds of databases and file systems. So for example, in this case, you can see that from using Spark, we are talking to HDFS, we are talking to HBase, and we are talking to Hive, and we are talking to Tachyon, and we are basically reading data from all these data sources. And then, so using Spark, we can interact with so many file systems. All right. Now, also note that just like in MapReduce, we had this data locality. While we were executing our code in MapReduce, it was taking care of executing my code near the file system, near the file, near the actual content. Same is true with Spark also. I'll show you the architecture. So there is something called Spark Core, which has many drivers using which you can interact with so many file systems. All right. And so one form of interacting with Spark is that you directly code against MapReduce of Spark, or you could use existing libraries. Okay. Existing libraries could be MLlib, GraphX, and there are some more libraries of Spark. And yeah, so all right. So there are some more libraries of Spark, such as one is GraphX, MLlib, and we have, uh, so one was, all right. Then there is a streaming library using which you can handle really fast incoming data. And in what all languages can you talk to Spark? You can talk to Spark in terms of Spark R or SQL, or or you can talk in Java, in Python, and Scala. Okay, so you can use either of these languages, R, SQL, Java, Python, Scala, to interact with these services. Okay, or and you can use the interactive command line of Scala or Python so that you can directly talk to Spark. Okay, so this is a little theory and architecture. We will we will get into more details now. All right, so this is wrong. So already installed on CloudX Lab. All right, and yes. Okay, so let me open. All right, so this is our console, and in case of CloudX Lab, it's already installed. All right, and the interesting part about Spark is that you can Simply download Spark binary from their website and launch Spark from the console without having to install anything. It will run in a sudo and local mode. You may not experience how does it run against Yarn. Okay, so if you have a Hadoop running already in your cluster, if you already have a Hadoop running in your cluster, you can download corresponding Hadoop version from their website and then extract it and run it. All you have to tell it is you have to just run this command. Okay, and that's it. All right. Also, in here, you have to tell if you want to run local or you want to run against yarn. So if you say minus minus master space yarn, then it should run against cluster. All right. So in our case, whatever we have here, so if I run PySpark, this is our Python Spark, the Python binding of Spark, meaning it's basically a thin wrapper over the Spark written in Scala. So that's why we can interact with the Spark from Python. So whatever command we execute here, it goes to the Scala version, and then we get the outcome. Okay, so um, that's why people think that PySpark might be a bit slow, but you can get your work done really, really quickly. It doesn't matter much actually. Okay, the performance is not too drastically different between the two, PySpark and Scala version. I'm keeping myself limited to the Python Spark because only then I'll be able to explain you very quickly. Otherwise, we'll get stuck in the language semantics. Okay, so Python is a far more simpler language than other ones. Therefore, I'll be limiting myself. Yes. Srinivasan question is any Java version of Spark available? Yes. This also had Java version. So again, you can write the Spark in Java, and just like MapReduce, here also you could do Spark Submit. And Spark Submit will take your Java program and submit it to the yarn. Okay? So you can run Spark Submit with the Java, yeah, whatever Java program you create, and it will take the MapReduce from there and run it. Okay? So I'll not get into the details of Java Java version. Okay? I'll just focus myself to Python version. All right. So this is interesting. So, all right, a little step back here. So right now, what exactly are we doing? We have launched the command line of Spark. And what does it mean by command line? Command line means using this interactive kind of a command prompt, we can write our program in Python. This is basically this is basically a Python console. It is basically a Python console. You can see that you can write your code something like x equals to 3.3 plus 4 and see you are able to execute the statement quickly. Similarly, if you have to write a function like def f and I'm saying my argument is x, you can do things like return x into x into x. So this is a Python function. I'm creating a Python function called f, okay, which is taking an argument called x, and then I'm returning x into x into x. Okay, so I could say things like this. See that? It has quickly multiplied 10 with 10 with 10. All right, so, okay, all right. So you can see that with 20, we have been able to multiply it quickly. So Python, for that matter, is the most simple language. If you have no experience in programming earlier, I think the best way to start is with learning Python. And I'll be making my Python classes recordings public. Okay, it's just that the session is under the is going on, but I can definitely make my Python program public from the other classes. All right. Now we have F40, for example, here. So you are able to multiply, you are able to call this function very quickly. Okay. So this is our Python console. Now this is our usual Python console, just with two differences. Here we are given two extra variables. By default, while Spark, this command prompt was being started, at that point of time, these two objects were created. One is Spark context, other is SQL context. Now these are, SC is your gateway to Spark. Otherwise, it is just usual Python command prompt. Other than SC and SQL context, the whole system is just usual Python. Okay, so we have SC and SQL context here. Now SC is your gateway, and we will use it a lot. Okay, now so up to here everybody is clear. Okay, right now we have started interacting with this by launching this command prompt. Okay, so now from here, from this command prompt, we could load any data from anywhere, or we could load data from and anything we do here will end up running either on Yarn or, okay, it will be running on Yarn because in our cluster we have configured it to run on Yarn. All right, now that's about the Spark, getting started with this Spark. So this is our Python program, which means we don't have to learn a new programming language, or we do not have to suffer with the limitations of new programming language. It's a full-fledged programming language with which you can do anything. It has functions, it has loops, it has classes, it has objects, and it has all kinds of libraries for manipulating data structures. Okay, therefore, this Python console gives you enormous power to do anything. And for that matter, the one which we have recently finished a Spark streaming exercise. I'll be writing a public, kind of small book on how to do the Spark streaming. So we recently finished a project with Dell where we did the Spark streaming using Python itself. So we were able to do almost everything. There was nothing for which we had to go back to Scala or Java. Okay, so although Spark was written in Scala, but that does not mean that we have to write the program in Java. Okay, we can get your work done in multiple languages. Also note that anything which runs inside Yarn is, at the end of day, is basically Java. Okay, so we write our code in Python that gets run by Spark, and then all of that runs inside the Java virtual machine. Okay, all right, all right. So that's about it. Now let's get into little more hands-on. All right, so here we are. The so the idea of Spark revolves around a data structure. This data structure, meaning structure of the data, in which we will be talking to this data structure most frequently. Just like in Pig, we load the data set, right? A equals to load something, right? So A is a data set. Similarly, in case of Hive, we have this representation of a table. We create table in the beginning. Similarly, if you are coming from a background like R, first, you all talk about data frames. You operate on data frames and vectors. So those are the data structures. So in almost every languages where data is of more importance, data is the focus. They all have a representation of a big data. Okay, In some cases, it's not that big. In case of databases, a table can go up to maybe a billion records, or maybe more. Okay, so everywhere there is always a representation to represent a huge number of records. Okay, so Spark's whole idea revolves around a similar data concept called resilient distributed data set. So this data set looks like a usual array to you. Okay, it's like a usual array. What is an array? Array is a big list of things. Okay, it's a big list or big array here. Okay, so this looks like a big array. You can see. All right, now what is the role of resilient distributed dataset? Resilient distributed dataset essentially is an array which is located on multiple machines. Like here, this RDD, this it might be having maybe hundreds of elements. All right, so maybe it might be having elements inside it, lots of them. Okay, but it's located on four computers. It's located on four computers. That's what it's trying to show, that there are four nodes here for which are holding this data, and these four nodes may be on the same place where our actual data is. So RDD is not something where you. All right. So there's a question from Rohit. Rohit says that in case we write Java program for Spark, is the structure and semantics same as MapReduce program? The semantics are different, but the philosophy is same. Semantics are different. Okay. All right. Now, so an RDD is basically a big distributed data set. RDD can be persisted in the memory. RDD can recover from node failures. It can have any data types but have a special data type for key value pair. Okay, we call that tuple. And then it supports two types of operation like transformation and action. And RDD is read only. Okay, keep that in mind. It's just a read-only data set. It's not like a database table which you can modify. Okay, so RDD in many senses, in many ways, it resembles our data set from Pig. Okay, so the only difference was Pig was not persistable. Okay, so RDD can recover from node failures. Okay, in case one particular node fails, it will it will reload from the beginning on another node. Okay, so the most important thing to remember about RDD is it's made up of many computers. So your data is loaded onto many computers, and you think that it's a simple array to me, and that's the quality about whole Spark API. It gives you all the functionalities which are stitched around the RDD. Okay, so let's try to create our first RDD. One is you take a local array. How do you define an array in Python? You can define, say, my array equals and put square brackets like this, and you can also put any data type inside it. Okay, and then once you've created this array, this is your local array. Okay, it's not yet Spark RDD. Now converting that into Spark RDD is like loading a file and putting it on multiple computers, or converting this my variable into a distributed representation of data called Spark. Spark RDD. Okay, imagine that had this array been really huge, say uh, maybe something like 30 GB. Okay, and you have great machine which you could load it on one node, but you have to parallelize it now. So you could simply I mean, parallelize, I skipped ahead a bit. So yeah, so you have got this big variable in memory and you want to convert it into distributed. So all you have to do is, let's say RDD1. This is the name which we are giving to our first RDD. And we are saying sc dot parallelize my array. Okay, now this RDD1 is is basically an RDD. You can see that this particular variable is basically an RDD, and the way you talk to RDD is in terms of transformations and actions. We'll talk about transformations action in a minute. So let's just see what is there in it. So you can see that the moment you interact with it, you start getting all of this. It's basically executing your task of bringing the data parallelly on the node. All right. At the same time, you could also load data from HDFS. Okay. Let's try to do that. I'm just going to rename it a bit because the lab has CloudX has changed since the previous session. So we're going to say cloudxlab.com. Or let's just say A. All right. Now we go here. So lines.take. Let's see if something happens. So what we just did was we tried to load data from HDFS. Our file is located here. We could also have said simply without telling that it's an HDFS, it will still consider it as the HDFS file. Okay, let me just see if that is true. Did it work? The input file, yeah, it did work. So this file, if you remember, I hope you are familiar with this file. This is the file on which we did the word count. Okay. All right. So what we have right here, what we did just now, okay, what we did just now is something very the beginning of all of this. Okay, so we try to load data from HDFS. If you have to load data from local file system, that's really not possible as a matter of fact, because your program, anything you run here, it's going to run in the yarn on multiple machines. Okay. All right, so what we did here just now, we tried to load data from HDFS. We tried to load data from HDFS into an RDD. Okay, so when we say sc.text file, it's going to talk to HDFS, find out where are the various parts, and accordingly, on those nodes, it is going to load mark the data for loading. And the moment we say, the moment we say RDD1.getData is going to get the data from those particular nodes. So generally we don't have to bring data back to your node. For example, here you don't need to bring this data locally. Okay, I think we are in time, right time. Good. So in previous case, you must have seen that one of the node I think has gone down. Okay, one of the node has gone down and it says that socket is closed, which means one of the node on our cluster has shut down or something has happened, an error has occurred. It immediately gave the work to somebody else and got it done. Okay, so so you can see that RDD is also resilient, meaning in case while reading this file, the one particular node on which we loaded this file, if that has gone down, it will load the same thing somewhere else. Sounds good? All right. So we just created an RDD called lines by reading this file. And while we are reading this file, your question could be, your question could be that that what is the individual object in case of RDD? As we talked about, RDD is more like a big array. Okay, so now your question would be, when we load the text file, what will this big array contain? This big array contains one line in one particular object. So this is an array of lines. When we are loading the text file, it's an array of lines. All right. Now on top of this, this is lines. You can see that it's a different RDD. Earlier one was the different RDD. So because this one has been loaded from HDFS and other one was converted from in memory. When we say converting an in-memory data into an RDD means taking this data, distributing it onto multiple computers, and then doing something about it. And what is that something? All right, there are some questions. Let me try to answer. So Srinivasan question is any version of Spark. We have already answered. So Harita's question is, since we did not say parallelize. Okay, let me open an editor. All right. So class notes, this is our, okay, December what? December 5. Okay. Now question is, since we did not parallelize, will it distribute? Yes. The text file, text file also do the same thing. Okay. What is 10 in case of this? So as we told just now, lines is a representation of that whole file in the form of RDD. Now, to interact with lines, we cannot just, get the data. We'll have to bring the data from various nodes to this node. And for that, we have these methods like take. Okay. And while we are saying, give me 10, we could also say take 1000. Now, this time it has given me 1000 lines. Okay. It has given me 1000 lines this time. Earlier it was showing only 10 lines. Make sense now? Harita, Dilshad, and Srinivasan, was I able to answer your question? All right, great. So this way we were successfully able to upload the data from HDFS and into an RDD, as well as we were able to convert our in-memory data into RDD. All right. So this is where we are. Now let's move further. Now what can you do on top of this RDD? We are happy that we are able to create something called RDD1, okay, or let's say lines, okay. So what all could you do? Do you have every ability to do? So in case you say lines.take, it will bring the data back. It's just opposite of parallelizing or doing the text file. Okay, so if you say take and you bring all the data, say 1 lakh records, the local computer's memory might get overflowed. So keep that in mind. All right, so on top of RDD, we can do various kinds of operations. There are two vague categories. These are two big categories under which the various functions have been classified. What can we do on top of our RDD? You remember in case of pig, what we could do? We could do on top of a data set, we could do filter by, and then we could do things like group by, then we could do join and other things. In the similar fashion, we can also do many things on top of RDD. We can do join, filter, and everything. You can do map. Okay, and all of these functions are part of two big buckets. One is called transformations. One class of functions are called transformations, which basically translate one RDD into another. They do not bring the data back, and they basically translate one data to another. Okay, so one RDD will result in another RDD. All right. So Spark transformation is something like this. Okay. So we do some operation, work on an RDD, it creates another RDD. Okay. This transformation creates another RDD. And this transformation, whatever you do, this transformation is going to run on all the nodes parallelly. It is going to run all the nodes run on all the nodes parallelly. Okay. So there are many kinds of transformations. Okay. There are many kind of transformations, and out of that, map, filter, flat map, and group by are just few of them. Okay. Now let me try to show you what does it mean by. So Rohit's question is, how did it separate each line? By default, delimiter was /n. Okay. By default, delimiter was /n. Okay, it's actually using the same input format of Hadoop. All right, now let's start with the transformation. Now we had this nice RDD. Okay, now what we want to do is we want to pick its we want to reverse each of the line. Okay, let's say we want to reverse each of the line, and there is a function called reverse in, I think it's there in Python. What was that? Yeah, also, those who are not aware about Python, who they can simply do dir, and it will show you. It'll show you a way to. It will show you all the functions which a particular object supports. So right now I'm looking at the functions which string supports. So it has to upper L strip. Okay, okay, yeah. So. All right, never mind. So we'll do something else. So we have these lines which are plain text file, and now let's say we want to we want to basically pick up first four characters of each line, and then convert that into uppercase. That's what we want to do. All right. So all right. So again, let me do a little recap. So there are many functions called transformations. When we give that transformation function, it's going to run that function against each element of array. So whatever transformation function you give, it is going to run that function against each element of the array. And in case of map, is going to translate one particular object into another object. Okay, so your function here you can see clearly that the Spark transformation called map takes an argument function. So it takes the argument another function, and we are basically passing, we are handing over our code to map that, hey, here is my function, can you run this function against each element of RDD. So when I say things like art, lines dot map, and I hand over a function to it by the way of argument here, this is the argument. So by the way of giving this object as like a parameter to map, it's going to run this particular function we are handing over to map. It's going to run that function against each element of RDD. Okay, so let's try to create a function. Let's define my func. Okay, it'll get some line in an argument. Okay, and what do we want to do with this? Let's say we want to do is return line, and we say give me 4 colon this, not 4 colon this, up to 4 characters. And then I'm just saying pick up the first 4 characters, and then okay, all right, so we have just created a function which will pick up the first 4 characters and then translate it to uppercase. Let's test quickly whether it's working or not. Okay, let's test quickly whether it's working or not. You see, it's working perfectly fine. All right. All right. Is everybody with me? So we have just created a small function which takes a string and converts it into another string. Okay. Now let's apply this function on all the lines of our RDD. And how do we do that? We say lines dot map and my func. And let's say first 4, okay, we call it f4, first 4 equals this. Okay, now you see that we said lines dot map and we passed the function and entered, right? It returned quickly. So question is, did it finish so fast, or it did not do anything? The answer is it did not do anything. It just noted that okay, f4 means this. It's a lazy way of doing things. Just like pig, it is also the whole behavior of Spark is kind of the lazy way. Lazy does not mean slow. Lazy means we will evaluate things when required, not right now. So the moment we say f4.take, just like in pig, we said uh, dataset.dump, only then it starts evaluating. You see that? It has evaluated really well. Okay, so it has just picked the first 4 letters of each line and converted it to uppercase and given it to us. Make sense to you? So we were able to do the translation or transformation of each object in an RDD into another object and forming another RDD. Okay, so map is clear to everyone. So just forget the usual map reduces map, Hadoop map reduce map. We're just talking about the Sparks map. Sparks map comes from the classic definition of map reduce, which came from functional programming language. Functional programming language has this concept called map and reduce, which was exactly what Spark does. Okay, okay. Pankaj's question is, what is U in this? Okay, so it's a okay. What is okay? Basically, in Python, when your string is Unicode, This is how it is displayed to you. If it is not Unicode, something like, let's say this, okay, let's say your variable x equals to, okay, this is not Unicode. In those cases, it will be displayed like this. Also, you could specify a string as Unicode like this. Unicode is a format of the string, format of the characters. Okay, how to convert? Basically, any encoding means how do you represent the bits in terms of the characters. Okay, at the end of it, everything is stored as bits. Right? So it's like a flag on string which says that this data is in Unicode. So please format it that way while displaying. All right. So that was our map function. Now there's a question from Rohit. Question is there any limit on the input size for processing on Spark since it is in memory, in memory processing of data? So, all right. So it does some of the data in memory, but if it is not able to keep the data in memory, it keeps in the disk. So you don't have to worry about the memory overflows. All right. Very good question. Very good question. All right. Keep going. All right. That means you are paying attention. All right. So we were able to do really interesting things like we were able to load the data in the memory and then translate it into something else. Now, let's say instead of this, let's say we want to do something else. We want to do something like um, give me all the lines which are starting with uh, or the lines which have exactly 5 characters in them. Okay, so let's say we want to do is um, okay, find out lines having only 5 characters. Okay, out of this big file we have, this is what we want to do. So in those cases when you have to so if you notice that when we say map, our input and output have same sizes. So if I say lines dot count, okay, it has got these many lines. 1,28,000 lines. Okay, 128,000 lines. Okay. Now in here F4 F4 was the one which was created like this, right? F4 dot count. So how many now also the F4 as well as that one both have the same number of lines. So the conclusion is that map basically results in the same size output because it's applying the function which you have provided to it on each element, and this function is giving only one value and it's preparing a new RDD based on that. Okay, keep in mind the most important thing is this map when we run it, this function when map runs our function, it's going to run in the network. If you have 100 computers, it might end up running on those 100 computers based on first, based on uh, how spread is your data. Second, it is based on your choice as well. You can say that this RDD need to be partitioned in 100 partitions, or this whole RDD should be loaded on 200 machines. So we can do that by saying partition. Okay, now that is another transformation anyway. So we were talking about the map, and then, all right. So sometimes you want to ignore certain records and you want to keep some records. So you must have some criteria on which you want to keep the record. Okay, that criteria is expressed as a function. Okay, that criteria as is expressed as a function. So you write a function which basically evaluates an object and gives true or false. So this function will tell whether to let an object go into output or not let it in the output. For example, we only want, in our case, we only want those lines which have 5 characters in them. So we are writing a function which will give us uh, which will tell us whether a line is a 5 character or not. Okay, so we'll say return length of line. Okay, so this is okay. So my func, and then I say Sandeep here. So it has given us 7 characters. That's right? Now let's try to create a function called only is 5 chars. Okay, that's the name of our function. And what it will do is it will return, or let me just make your life simple. If length of line equals to 5, okay, length of line equals to 5, return true. Okay, and then if it did not return earlier, then it will return now false. Good. Now let's try testing it. So when I say this, it says, oh, so let me change this bit. All right, let's try it again. Is 5 characters or not? That's what it is going to tell us. It says false. Okay, now it is true. If it is bigger than this, then also it's false. So basically, we just created a function which tells us true or false. Okay, so this function we will be utilizing this function as a filter. So we will say lines dot filter and is 5 characters. Okay, so we'll say 5 character lines. Okay, 5 character lines. So again, it hasn't done it anything yet unless we say take. Either we can collect or we can say take. You can see this is 5 characters. Do you see? Wow, this is 5 characters. All right. We could also say something like, and if you want to find out how many such lines are there which have 5 characters, we could say count. So it's saying there are 1150 lines which are of 5 characters. All right. Okay. So there is a question from Peter, and it does make sense. His question is, why would somebody like to use MapReduce when Spark is so much more effective? Okay. So first is that when it comes to batch processing, when you have to do a lot of things, I mean, churning terabytes or petabytes of data, you you would like to use the the traditional MapReduce still. Okay, a traditional MapReduce is far more better at churning a lot of data, far bigger data. And the other benefit of traditional MapReduce over Spark is the traditional MapReduce does not consume too much of memory, while Spark seems to be consuming a lot of memory. And and it might at times it might make your cluster really really busy. Okay, so in cases of batch processing where you don't have urgency, you you can afford to run in MapReduce so that your memory is not consumed too much. So in case of batch processing where your requirement is not immediate, say your daily jobs are running, and daily jobs are running, for those daily jobs you need to do kind of daily you don't need immediate output. For those you should generally go with MapReduce. Now the next question is that why did we the other aspect of this question is, why did we learn MapReduce when we had Spark and these kind of things? The idea is that the under the hood, the MapReduce paradigm, where instead of we iterating over the data, we write these functions which translate the data from one form to another and hand over to the platform. That paradigm needs to be learned. And MapReduce paradigm did a very great job at teaching that paradigm to everyone. Okay, so those are the two main aspects of learning, learning and using MapReduce, even though Spark is fairly effective. Okay, was I able to answer your question, Peter and everyone? Because this is a very good question actually. A lot of people ask it. Okay, so for that matter, one of the interview questions which I had written here in my blog post. Uh, okay, so my this Apache Spark's interview questions are fairly popular. I mean, they come on the page rank one. Okay, so and yeah, coming down, coming up. Yeah, here I have written that part. Okay, yeah, here. Is there any point of learning MapReduce then? All right, so go through it. You can try it out. All right, so that was the way we could use filter in order to filter certain data from RDD. So right now we are just taking baby steps. Okay, later point of time you don't have to generally write MapReduce. You can either use SQL, okay, or use these next level tool like Spark SQL to do the churning of the data. All right, now moving ahead, where is the data? Yeah, here. Now sometimes you want to convert an object into multiple object. Like in our case of Hadoop, when we broke a line into word, right? One line gave one key value, one input key value gave more than one key value, right? If you remember our discussion. So if you have to do the same thing right now, each of our element in an RDD, our RDD right now is composed of the lines. If you want to convert these lines into words, what will we do? Okay, in those cases we will use flat map. What does flat map do? Flat map basically takes your function, apply that function on every element of the existing RDD, and whatever is the result, it expects the result to be an array, and it picks up the values of an array and then forms the new RDD. This new RDD, in case of flat map, maybe will have more number of elements. Will have more number of elements than the input. While in case of map, So in case of map, the number of elements in the output will be equal to the input. In case of filter, the number of values in the output may be smaller than the input. Okay. In case of flat map, number of values in the output may be more than the input. Okay. Let's see this in effect. All right. Now let's say we want to convert our RDD, which was RDD of lines. We want to convert it into RDD of words. Okay. So we say words equals to. All right. First, we have to create a function. Let's say create a function. We just created. Let me give proper names. Let me give proper names. Two words. Two words is our function, which will take in a line in an argument and will return the words. Okay, so we are going to say lines dot split. Okay, so this is the function which can do wonders. And all right, sorry. Okay, so it will be two words, and it did not. Oh, I did not return. All right, all right, so here we go. So let's try to run this again. You can see that it has splitted Sandeep space Giri, a single string, into two strings. Okay, we will use this function. We will use this function to convert our lines into words. We'll say words equals to lines dot flat map. Note the flat map, and we'll say two words. Here we are kind of passing the function definition, handing over the function definition to the flat map. Now let's just take 10 elements. You can see that it has broken down the line into the words. Sounds good? Sounds good to you? All right, you can see that here. All right, now let's see words dot count. Okay, so you can see this time it has around 1.1 million words. Okay, so we have been able to successfully convert the RDD of lines into RDD of words. What does it mean? Earlier our array contained each element of array was a line. Now each element of the array, in the new array, if I call an RDD an array, new array is basically containing one word as an element. It's an array of words rather than lines. Okay, so we are able to successfully use these. Now there are many more functions. There are many functions which are transformations. Things like group by key. We could group these elements using the key. All right. So there are many more examples of the available transformation. You can see that. Also, if you want to see what all functions are available, this dir will do a very good job. Okay. So if you see here, what we have done is we have said dir words. It gives us all the functions here. Okay, all the list of functions. Don't touch those underscore functions. Those are internal representation of various operators. Okay, so and you can also say things like this and words dot zip with unique id. So it shows you what does the method do. Okay, this is probably the best way to explore any API. Okay. Now, question from Harita is, what would be the result? Very good question. Let me try writing it. Okay. So the question is, let's say we said words one equals to lines dot map, and we did this, right? That's what you mean. So instead of flat map, we are doing this. Okay. And let's the next thing we'll do is words one dot take 10. All right. What will happen is each element, the RDD will still be composed of RDD will be composed of array of words. You can see here. I'll show you. All right. Now let's run it by saying take, just like we used to run in pig by using. You can see here. Now let me take it out. I think that will be better. So now your RDD, each element of an RDD is an array. You can see each element of an RDD is an array. Make sense? So our RDD is not made up of words. Instead, it is made up of array. All right? Good, good. So it is basically an array of arrays. That's what it is. It's an array of arrays. You can see that this is an array of arrays. Okay, good. Brilliant question. Now moving ahead. All right. Now, till now, we had been talking about transformations. In transformations, every transformation resulted in another RDD. Transforming an RDD resulting in another RDD. Sometimes we want to get the results. Okay. The way when we said take, it did something. So take was an action. Take was an action. So this is the another class of functions on top of RDD which do some action. Okay. So when we have to do some action such as get the data, save the data to the disk, or something like that. When we want results, in those cases we run action. At this point, when you say run an action, everything on which an RDD is dependent, this RDD, say for example, words was an RDD which was created out of lines, right? And lines was an RDD which may be created by something else. So the moment we say words dot take, we are basically calling an action called take. And what will happen under the hood is then the evaluation of this particular RDD will start. All the RDDs on which this depends will get executed in sequence. The first one, which depends on nobody, will get executed first, and then the rest. Okay, so it's basically a directed acyclic graph. All right, so that's what an RDD is. That's what an action is. There are many actions. So, for example, we have been using an action called count so far. So, in the same way, okay, so when we say reduce this, okay, aggregate element of data set using a function. So now there is an interesting understand. We need to understand few things. So all right. So that was an action, and the most simple example of action is count. Count. So for example, words dot count will words one, the one which we did just now, it will give us 1.28 lakh records. You can see that it is not 1 million. Okay, so this count or take are a classic example of actions. Now there are some interesting actions such as reduce. Okay, this reduce basically is like combiner in case of Hadoop. It takes two argument. So reducer basically reduces the whole array into a single object. Okay, reducer reduces the whole RDD into single object. All right. Now, and this function which is taking this function takes two arguments and convert it into a single value, and it does it. So your question might be that while this function is taking two argument and giving only one, how does this reduce convert millions of elements into single, right? Reduce might convert the whole millions of values in an RDD into single value, while function basically converts two values into one. Let me show you that. So let's say we want to do something like um, what was the one which we did? Let's say uh, yeah, let's say that in case of words, right? We had words. Words has so many big array, right? Now, what we want to do is we want to compute the total lengths of all the words. Or let's say we want to find out the biggest word in this file. Okay, we want to find out the biggest word in this words. And all right, so let's say we want to find out the biggest word in this array, this RDD called word. So what we do is we define a function. We define a function called bigger word. Okay, word 1, word 2, and then we say return if if length of w1 is bigger than length of w2, return w1, else return w2. Okay, so we are basically uh, finding the bigger word out of the two words. So out of Sandeep and out of Giri, it will give us the bigger word, which is Sandeep. Okay, now if we keep on increasing this, now this will it will return this. So now you see this bigger word is taking two arguments, returning one. It's like a machine which is having two input input flows and returning one output. Okay, so the bigger word is returning in one value, right? Now how does this so we can, if we run so we can say biggest word equals to words dot reduce. Okay, and then we say all right, so now biggest word is this. Okay, so this is the biggest word in the line in the file. All right, so basically just like our combiner, reduce is going to apply your function again and again on two values until it converges into one. Okay, it will basically keep running your function again and again on top of these values until the whole thing is one, right? So first there will be 100 element, then there will be 50, then there will be 25, then there will be then there will be 13, then there will be uh, not 13, there will be 25, then there will be 14, there will be 7, then out of 7 there will be 4, and then out of 4 there will be 2, and then there will be 1. So that way it'll keep on applying your function unless it converges to 0. Okay, so that was our reduce function. Okay, now what goes on in the backend? Let's take an example uh, of this particular case. So we will talk about it after the break. All right, we'll talk about it after the break. All right, so should we start now? Zuan says that there is a delay with the connection. Is there a delay? So I'm selecting single node, node 1, node 2, node 3. Is there a delay? All right. So there is another question. All right, all right. Zuan, is there a delay? I think there's no delay. It just because I deleted first and then I spoke a little later. All right, that might have given you an impression. All right, so there's a question from Rohit. Question is like Pig or Hive, is Spark also converted into MapReduce internally? So not really. It's not the traditional MapReduce, but every other library which depends on Spark, it'll be converting the things into transformations and actions. Just like the way all the libraries that depended on MapReduce, Pig and Hive, they converted their code into MapReduce. Similarly, Spark is all the libraries that are dependent on Spark, those functions internally get converted into transformation or an action. All right. So this is where we are. All right. So there is a quick, an example on what is going on. Okay. So let's try to show you what is the code about. Let's say there is a lines which we loaded, then we created something called line length function, which takes argument as line and does say return length of line. Okay, now what we do is line length equals to lines dot map, and we say LL. So it'll convert our lines into line lengths. Let me increase the font a bit. Okay, okay. So we have converted our lines into line lengths. Okay. Now let's say we want to sum up the line lengths. Okay. What we'll do is line lengths dot reduce, and we will say sum. Okay, what does sum do? Sum do define sum, and we say sum equals to x1 x2, and it returns or let me just do this. Okay, returns x1 plus x2. Good. Now so this is what's going on. We are saying we defined a function called LL which computes length of the line. Now we executed this function called LL against all the elements of this RDD called lines. Now we got another RDD called line lengths, which is nothing but of the same size as the input RDD called lines, but each element is the length of the line. Length of the line. Each element of line length is a length of the line. Now, if we say create a function called sum, which basically sums up two values, and we say line length dot reduce sum. Okay, what will it do is it will run this sum function against two elements of this big array until again and again until we get a single value. Okay, so so sum equals to line length dot reduce, right? Now here, okay, so sum will be a single value. It will not be an RDD because reduce is an action. Okay, so let's try to. I think we can execute this right away. Okay, we can execute this right away. All right, I think it should work. Okay, now I'm defining a function called sum. Yes, and I'm saying, all right, I will say line length. What does it say? It says x2 is not defined. Yeah, because of this. All right, and let me try again this. All right, so it has computed the sum of all the line lengths. All right, so this is what has happened. Now let me try to show you what would have gone under the hood. Imagine that your lines is containing these many values, and had it been simply these many lengths, so the summation could have been simply 62 on a single node. If we were not using any Spark, this could have been the result. Now imagine the same array being on three nodes, node 1, node 2, node 3. As we told you that an RDD is loaded on multiple nodes. So some part on node 1, some part on node 2, and some part on node 3. Now on node 1, let's say the first three objects are there, right? And on first three, when so individually on each node, the same process is going on. The moment we say, give me line lengths on node one, when we said, give me line lengths, we would get something of this sort. Then when we say sum, so what will happen is it will sum up these two values, it'll become 20, and then again sum it up, sum these two values, and we'll get 24. Now, on node 2, there is only one value, therefore it will be only 14. On node 3, when line lengths get summed up, you'll get 24. Now, the driver node or launcher node or somebody or from where you are launching right now, we are the driver here because we are running the command line. So on the driver node, all these three values will be brought on that driver node. So 24 from node 1, 14 from node 2, 24 from node 3 will be brought to the driver node, and there again the reduce will run. Reduce in the sense that your function is being run on two values at a time again and again until we get one value. So 24 and 14 will be added, and then 38 plus 24 will be added, and we'll get the final line length. So that was our way of representing what's going under the hood when we are saying things like this. Okay, so was I able to explain what exactly happened? Okay. I have put it into this notes files also so that at later point of time you can have a look. All right. So yeah. So Rohit and Dilshad, Harita, Pankaj, Peter, Shashi, Srinivas, and Sumati, was I able to convey what I was trying to convey? Okay, so all right, great, great. So everybody clear about what's going on with the Spark? So Spark is basically providing you these transformations and actions in the core API, which you can utilize to do the distributed computing. If you don't want to do distributed computing, you can continue using your Java, Python as usual. And whenever you want to, run some code against big data, you can load that data into Spark and do some computation on Spark, and then you can basically quickly stitch all the phases together. All right. Now, the just like this distributed cache in case of, so what does distribute cache did in case of Hadoop MapReduce? Whenever you had to take one file or one piece of data to all the nodes, you could put it in distributed cache and send it to all the nodes. Now, Now, in the similar way, sometimes you want to broadcast things to all the nodes. Okay, in those cases, you can simply say SC. SC is our gateway to Spark. So you could always say sc.broadcast and give a big object, and that object will be taken to all the nodes efficiently. So this is how you can inform all the nodes quickly. Okay, this is how you can inform all the nodes quickly. And next is accumulators. Accumulators are way of each node reporting things. When each node need to report their progress, each node need to say continuously give you the status report of what's going on, then you can use accumulators. Accumulators are part of the Spark context. So you could always create an accumulator, and everybody in the network inside their map or reduce functions, they can keep on writing to accumulator.add, accumulator.value, and so on. Basically, all the nodes can pipe the data to the central node in the real time. Okay, that is the role of accumulators. All right. Now, this is an example of word count. You should go through it. Okay. So we already have lines and words. Okay. We have already prepared words. Now, let me try to explain what's going on here. Okay. So, one thing at a time. So we loaded a file called h1.cloudxlab.com. Okay. Just like this. And then, what was the file name? I think it was different. Yes. All right. Here. Yes. Here. Yep. This one. And you could also say things like my out. Okay. So I'll just go with one thing at a time. So is the font clear to everyone here? Do I need to increase the font? All right. So you can see here. All right. So here what we did in the first line, we loaded data. If you do not give HDFS, if your Spark is running on Yarn cluster, by default it will think that you are trying to load the data from the HDFS. Okay. So we loaded the lines. That was the first step. Now we can quickly check every time we do something that is there something inside it. Yeah, you can see it has successfully loaded. Now, next thing we did was we converted that into the words by first splitting the line, and then calling that function which was splitting the line by using flat map. Now we got words. Now you could convert a word to key value pair. Okay. Now we got key value pair, words key value pair dot, let's say, take. What happens? So key value pair, when we have to create, all we need to do is we need to create something called a tuple. This is a tuple in case of a Python. So it's more or less like an array. Okay, so we have just created a tuple where there are key value pairs. Now we are saying we are running this. We have already run this tuple, is it? Yeah, we have already created tuples. Now let's create a function called sum. Okay, so we've created a function called sum, and now we are saying there is another action called reduce, another what do you call, another it's a transformation. It's basically is going to group, and then on all the values for that group it's going to call your reduce function. So we are saying WC equals to key value pair dot reduce by key. Okay, so that's where we go. Okay, so now it has started the whole process. So it has done a good job here. You see, when we said take, it has computed that. And then now it has saved the data into my SDFS folder. Okay, so that was our Spark. Let's just see Hadoop fs minus ls. Okay, so here, what was the folder name? My dash out. Did it save anywhere? Oh, it did not. No, we had to save as save. What was that function? I forgot. All right. So save as text file. Sorry. So you have to do dot wc dot save as text file and the folder name. It does not return anything. Okay, so let's start. Did we overwrite something? Okay, so what does it say? It says that it has created a folder called my out Hadoop fs minus ls. You can see here it must have created here, and then you could say things. Okay, all right, you can see part 1, part 0, part 1. Okay, the nomenclature they are also keeping in a similar way. Okay, Hadoop fs minus cat. All right, so it has computed the map reduce just like that. Okay, just computed the word count just like usual way. Again, question from Rohit is why did it create two output files? Very good question. All right. So again, as we were talking about that there is a partition in our input data. So it also respects that partition. Okay. So it is basically running your MapReduce parallelly on the cluster, and then it's saving the result parallelly. Okay. All right, just like MapReduce produced two outputs when we said there are two reduces. Okay, so that's what it is also doing. Good, very good question. All right, all right. Let's start with no. While loading, it automatically figured out that it has to create two partitions. Okay, good question. All right, now. Now, sometimes you want to do the broadcast, as in, let's say you want to remove these words from the word count. So, in those cases, you could broadcast this, and after broadcasting, you could also check. Okay, you could also here use this common word. You see here common words, and we could use it here in a filter function that return only if this particular thing does not exist in our list. Okay, and and then accumulator we have defined, and continuously accumulator is being reported that things are happening. You can see that. So we can utilize these kind of broadcast and accumulator to solve our problems. All right, so that was our quick g- pass through via Spark. All right, so all right, so at a lot in lot of cases, what we people realize that the Spark was fairly fast. Okay, Spark was fairly fast. What if we could utilize this ability to churn data really fast to process the input data, which is real time. Okay, so let me take a step back here. Instead of jumping into Spark streaming, let me try to explain what do we mean by streaming. Okay, what do we mean by streaming? That's a very common question. The difference is streaming does not mean watching a movie like YouTube streaming. No. Here, streaming does not mean streaming does not mean the Hadoop MapReduce Python streaming. No. Here, streaming means a lot of data is coming in real time and you want to process it right away. Examples of streaming could be that you are running your website and you want to see currently how many users are there on the website. Okay, you want to run that, you want to in real time, you want to compare that how many users are there on the website. Okay, so Spark streaming is basically solving that kind of problem. I'll give you my personal experience. So let's say in at Amazon, every time an item gets changed. Okay, every time an item is modified by the seller team, the people who are taking care of sellers. So item as in, let's say somebody made spelling corrected on the item, or some seller has changed the price, or somebody has added more photos, somebody has changed the photos, removed the photos. So these kind of changes keep happening across all the categories and across all the products. And now there are a number of things that need to be done in order to handle these changes. Okay, so for example, let's say a user has a seller has modified the image. There's a team called fraud team which basically checks whether image is good or not. Okay, similarly there is another team who want to figure out the latest updated image and they want to push it to the cache, or they want to push it to S3 in the real time. Now there are many people depending on such data. So instead of people writing in each other's code, what we do is the one all of the people communicate to each other by writing data into a queue, into a kind of a publisher subscriber big queue. And that's the role of a queue. A role of a queue is twofold. One is providing a data pipe as in On one end, there are many people writing to this data pipe, and on another end, there are many people reading from this data pipe. Okay, so one is that it's like uh, newer data is consumed first. Sorry, newer the data which came earlier will be processed first. Data which is coming now will be processed later. Okay, it's a standard queue way. Second thing these queues provide you is a publisher subscriber kind of model. If you want to inform all the people that hey, I'm done with the process, okay, I would use a queue. Similarly, in case let's say checkout process has finished. Now there are hundreds of things that need to be done by an e-commerce website whenever a user is finishing the checkout process and placing an order. The order database has to be updated. All the people need to be informed. The fraud team need to be informed that hey, an order has been placed. Do you want to check whether it is genuine or somebody has stolen somebody's credit card and has placed the order? Or there could be hundreds of team who are interested in this data. So this publisher subscriber model is a very important thing, and it is probably publisher subscriber and the data pipe both are very well solved by these queues. Okay, these queues could be Kafka, Flume, HDFS, ZeroMQ, or Twitter. There are many different kind of queues. So Flume is also a kind of a queue. We'll talk about it. All right. So this is our streaming. So in the Spark streaming, we consumed data from these sources and then write some output to maybe HDFS databases or dashboards. All right, that is streaming. Now, as part of almost every streaming system, we convert a window of time into a batch, a input batch into a small value. We say that, okay, give me last 10 minutes data and I'll convert it into something else. Okay. Otherwise, we won't be able to handle such a huge data. So most of the game in streaming is converting the continuous flow of data into batches and then converting these batches into single value. Okay, that's how it is. So for example, you might be interested in watching the per second number of users on your website. That you can do easily by gathering total number of statistics every second and displaying it. Okay, so Spark Streaming receives the live input data streams from various places like given in previous example, and then it converts this continuous flow of data into the mini batches, and after that Spark Engine generates final stream of data. So every batch is an RDD. Every batch is an RDD on which you can run your code. You can tell Spark Streaming that, hey, Spark Streaming, here's my transformations and here's my code. Run it against each batch. And then it'll keep on running on that batch again and again. And whatever is the result out of your program, it'll get saved somewhere. So that's the role of streaming. All right. So internally, so instead of RDD, we call it D stream. D stream is an object. D stream is a kind of an RDD, is basically a object representation of containing many RDDs. So D stream is a collection of RDD. And as and when new data arrives, there will be one more RDD. For each new data, each new batch, we have an RDD inside dstream. Dstream is the main representation. So when we run our code, say dstream.map is going to run that against RDD at time 1, RDD at time 2, RDD at time 3, and so on. As and when the data keeps arriving, it'll keep on executing our transformations and actions. Okay, so that's about stream processing. The stream processing provides a lot of things. It even provides us further changing the window size. we can further decrease our window size by combining multiple time windows together. All right. All right, so let's take a case of this is one case of counting the word per second. So the first step would be creating connection to the service. So here we are saying this piece of code is in Java, so be aware that it might look really ugly as compared to our MapReduce. I have purposefully kept it in Java so that those people who are from Java, they feel comfortable. People who are from Python can do it far more simpler way. Okay, so in the as the first step, you create a connection. You create a connection to the input stream. Okay, you might be you might want to read data from maybe a file system. Every time a new file is added to the folder, you can process it. Okay, that also is an example of streaming. As in, when files are getting uploaded into a folder, you want to process it. For example, when you use Flume, we'll use Flume tomorrow or today, whenever time permits. So whenever new data gets added to a folder, your it'll be considered as new RDD. Similarly, if new data is coming to a queue, there will be new part of RDD and will come as part of this streaming context. So here we are saying start the streaming context, start the socket by connecting to localhost at this port. Now it will start reading from there and it'll start creating the batches. And for each batch, it will create an RDD, and against each RDD, it's going to run your function. So here you're saying lines.flatmap. Lines is your this stream which you have got. Internally, it'll execute whatever you feed here to the on the RDD. All right. Here we are doing exactly what we did in case of our usual MapReduce. Just that only difference here is instead of the input being RDD, here the input being the D stream. So this is the stream on which our all of this logic is going to get executed. All right. So here we are converting our string into a key value by saying string is the key and value is 1, and then we are summing it up by saying reduce by key, and then we are saying word count by collect. So this is what is happening. So input data is coming in, and so many RDDs are being created per second. Why? Because here we have defined it like a per second operation. We are saying duration is 1000 millisecond. So it's creating out of the input data, it's creating the discrete RDDs for each second data. Every second it reads the data from input and creates an RDD. And then on each RDD, it's running our functions and generating the output. All right. So that was our Spark streaming. All right. So I don't have a running example right away for the streaming, but if you guys want, you can drop me an email and I can share with you another video of mine which is quite helpful, which basically demonstrates how to read from Kafka and do the MapReduce. Okay, that's from Big Data and Spark class. All right. If you are interested in streaming, then you can let me know. I can share with you that particular video. All right. So that was our Spark streaming. We'll talk about the rest of things maybe tomorrow. Okay. Today we are going to talk about few more things. All right. So that was our. All right. So is everybody with me, or have I put all of you to sleep? So Juan is there. Okay, Peter is with us. All right, all right. Great, great, great. All right. So in case you want to have a look at a Spark streaming example, a running example, just drop me an email. I'll send you the video that is around maybe more than 2 hours. Okay. So yeah, because that will take a lot of time to configure right now. All right. All right. So this was our quick overview of Spark. So all right. Now back to the little older things. Okay. All right. So we want to discuss now about the no the all right, back to our traditional MapReduce. Okay. And trust me, all of these tools are going to get translated to Spark as well, like Mahout is being translated. So all of these tools are on the way to be translated to Spark as well. So it's important to learn about these. All right. So what exactly is a scoop? In very simple words, when you have to pull data from databases onto Hadoop ecosystem, you need tools. Or you want to take some data, some structured data from Hadoop ecosystem to back to databases. You need some kind of a tool. Why? Why can't we do it ourselves? Because if you do it yourself, either you will end up running it on a single machine. Okay. So whenever we deal with this kind of data, we are dealing with huge data mostly. We are dealing with millions of records or hundreds of millions of records or billions of records. So while transferring the data from traditional databases to Hadoop, if you do it in a traditional manner, as in open a JDBC connection, open a connection to Hadoop, and keep on reading from the database and keep on writing to the Hadoop file system. Now, although logically is good, it will work, but in reality, it'll be really, really slow. It'll be very slow. And it'll be very slow, and we will end up with lot of overhead. Okay, we will end up with overloading one or two machines. So either we write a MapReduce program which basically distributes this logic of copying data from traditional sources or databases to HDFS, or we use Scoop. So Scoop is basically an open source tool which extracts data from structured data sources into Hadoop for further processing. It can also move data from DB to HBase, Hive, HDFS, and vice versa. It can also export data back to the database. And it has extension framework called connector. So in case you got a new database which is not yet covered, you can use this. Okay. So a quick hello is we have SSH. Let's try to do this. I'm not sure if it will work. All right. So we are already there. We are already there. Okay. Go to shell and do this. Okay. So we say here, do we have it installed? Looks like, oh, sorry. We have to say, all right. Looks like it is installed. Okay. Also, please note that I'll have to do a little bit hunting around to find out where is the MySQL. Okay, I might have to do a little bit more hunting around to do localhost 3306. Connection refused. Okay, so MySQL is not installed on local machine. All right, no worries. So to show you hands-on, I think it'll be a little challenge. All right, so when we say scoop help, it shows us all the possible commands. Okay, I'll explain to you what all those mean. So first is code generation. Code generation is generally it generates the Java code which has each class corresponding to each table so that you can use these classes to load the data and push the data back and forth. So this code generation is something we used to call it fact. Okay, long back when we were writing our own tools to translate data from one form to another, we always have classes representing the data and then a mapping between the data input and the classes. So this code generates such classes. Okay. Internally also, when we run scoop, it internally creates all of this Java code and runs it for you. Okay. Now create Hive table. When you want to import database table into DB, we do we have to create if you want to create Hive table automatically, we can use this. Let's try to do things rather than talking. All right. So we have these many commands. Okay. And all right. So a quick answer to the question that what does it mean by connector? So there are hundreds of databases in the world. Okay. To keep the commands same, to keep this tool generic, we use connector. Just like we have. So connector is basically a wrapper around JDBC database driver. So connector is nothing but a wrapper around database driver. Okay, so it's a very simple one. Whatever minimal things it requires, it is, and for that matter, there is already connector for almost every database. Okay, for almost every database we have connector. All right, now I have to do something about. All right. Uh, okay, so I'll have to find out. All right. I think what I'll do is I will do it maybe tomorrow. I think it'll be better to do it tomorrow because this database need to be created and I need to find out the password. All right. Let's continue with. Okay. So basically, in these commands, I think we will run it again tomorrow, each one of them, and then we'll try to import data to and from a MySQL database. Okay. Either we'll install MySQL somewhere where we'll put some data and then we'll try to import export it. Okay. All right. So let's continue with the Flume. Okay. So these are very small tools. They are just we are discussing it so that you know about it. All right. But there's always something great about some tools that need to be appreciated and learned. All right. All right. So let's talk about something called Flume. Okay. What is a Flume? Flume is basically a way of distributed and reliable way to transport data from many servers to HDFS. Okay, I'll tell you few use cases of Flume. You can use Flume. You can use Flume to download. Okay, let me tell you exactly where we used Flume. So we have these. We had in the ad server. We had these. The ad server is nothing but a web server. And when you think about an ad server, I'm talking about InMobi. So when you think about an ad server, you always have hundreds of servers running. Okay. In case of InMobi, we had around 20 very high-end servers, and that number kept on changing all the time. We kept on increasing every 6 months. Okay. So what we did there, so every server generates error message and generate access logs. Access log means who is accessing the website from where. And as I was explaining to you earlier, my project, one of my projects where I was doing the recommendation, was based on the access logs of Apache. So this data that who is visiting your website from where, what is their IP address, how many, what is the session ID, how is their flow, what is their daytime zone, and if you combine all of this data together, you can come to very interesting analytics. And that's how Amazon also shows the recommendation on their website, by churning their website logs. So the website logs are like gold mine for a data scientist or data analyst. And that's the first thing most of the engineers who are focused on big data work upon. That's the first entry point. So first you try to manage those log files, because every day even a medium-sized business generates lots of log files. So to process these log files, you need a central store, and nothing better than HDFS for unstructured data like log files, right? So what people do generally is they take these big log files from all the server and keep on copying these to a central place. Okay, they keep on copying this to a central place and keep it compressed, and whenever required they process this data, and whatever are the processed results, they store it in HBase from time to time. The question is, should we write our own program to read from all the servers parallelly and then push the data centrally, or should we do something else about it? If you try to write your own programs, it's very much prone to failures. Okay. Now, to solve those kind of problems, uh, people invented things like Flume. Okay, people invented things like Flume. So this example, what you see is from web server, the data is coming to the Flume agent. This is your Flume agent, this box, and then Flume agent is pushing data to HDFS. Okay, so Flume is basically a distributed, reliable, and available system for efficiently collecting and aggregating large data from many different sources to a central data source. Now, notice the distributed one. Okay, so all of the tools which we have discussed in this class are distributed in nature. Okay. Or for that matter, anything which is under the Hadoop umbrella in the open source, all of them are distributed in nature. Okay. Even Scoop was distributed because copying the data, it was distributing to maps and reduces. Now, all right. So I'm very much afraid to lose the recording. Alright, so I have stopped and started the recording again. Alright, now, so before we proceed further on to use Flume, let's understand what exactly is Flume. Flume is made up of agents. These agents, each agent is described as two forms. The agent is more like a USB cable, okay? More like a USB cable, and it has got source and it has got sink. Okay, source and sink. So the power, like in this case, why I've put it source, the power is coming from this side and going to the sink side. Okay, when you charge your phone, this is what happens, right? You insert here and goes to the sink. Okay, so so and there could be hundreds of connectors, hundreds of kinds of sinks. So all we need to remove, if we want to change this into something else, let's say we want to charge an earphone, okay, from the same cable, all we need to do is remove this side of cap and put the connector, put the sink which is of say type earphone, okay. Or if you want to load this the source is our DC adapter, we can remove this side and make it the DC adapter. Similarly, if we don't like this source and we are in the car, we can remove this part and put it. So I'm giving you an analogy. Then what does it mean by agent? Agent means agent has got a source and a sink. A channel is the wire. Now, the source could be changed. If we want to download data from Twitter, we'll use Twitter source. If we want to download data from our web server, from our particular port, we will use another source. If we want to just execute a command again and again, then we will use a different source. If we want to read data by tailing a file, what do you mean by tailing a file? We just do a tail minus f. That's a Unix command to read a file. And what does it mean? So when you say tail minus f, it gives you the last 10 lines of that file, and in case the file does not exist, it will wait till the file gets created, and it'll, as and when users are adding lines to this file, it will keep giving you that output. Okay, I could show you some examples of, oh my, I'm sorry. Okay, so yeah, so you could say things like where log, so let's say last log. Okay, so as and when new users are coming in, we will keep on getting more and more data here. Okay, so basically this is a good way. Okay, so it basically opens the door, this source and sink, this modularization, that you can remove source, put something else, pick some other sink, and then make it work. So this modularization is really, really very powerful. Okay, so if you have three different kind of source, three different kind of sink, you could basically create nine different kind of transports. Okay, now sync means the where will the data get stored. Do we want to store in database? Do you want to store in Hive? Do you want to store in HBase? Do you want to store in HDFS? That is sync. But by mostly the sync is HDFS. Mostly in case of Flume, sync is HDFS. All right. So you basically create these agents. And what is this channel? What is this channel? This channel is used as a buffer. Buffer as in, if source is writing at a very fast pace, this channel will be keeping the data, and sync will be consuming the data at certain pace. Okay, so generally when you have this producer and consumer, so the difference in their frequencies, you generally utilize a pipe in between them. For example, writing to the disk in bulk is faster, okay, while uh, writing from various sources could come at a very different pace. So when a source is generating a lot of small data continuously, the sync might take the data in big batch and purge it to the disk. Okay, if sync tries to store the data in 1 kilobyte size, it might be slow. The sync might get slow. So therefore, the difference in the frequencies or the rate of consuming and producing is compensated by this buffer. Okay, so if the ideal size of the buffer is where the total data produced in that time by the source is equal to the total data the time taken in the two is equal by the sink. Okay, so what I'm trying to show here is, here source is generating data 1 megabyte per second while sink is consuming at 60 megabyte per minute. Okay, although if you see it's the same thing, right? But since they have, if sync tries to write the 1 MB data, it will again take 1 minute. Okay, so that's why sync has this behavior. So those kind of differences are compensated by the pipe. All right, so that's what is an agent. It's a very important philosophy in any producer consumer, be it be it Kafka, be it any queue, or be it any distributed system. This producer consumer is probably the most important aspect, and it's the best way to run your distributed code. Okay. All right, all right. Now using these kind of agents, agent is sink, source, and channel. Using, you can combine them together and form a complex mess so that the data can flow in the way you wanted it to flow. Okay, so you can see here, we one sink is writing to another source, and one sink is writing to multiple sources, and multiple sinks are being consumed by a single source. So you could combine these agents together to create really a complex business. Okay, so Flume supports large variety of sources including tail, syslog, log4j. Flume nodes can be arranged in various arbitrary topologies as discussed in previous slide, and typically there is a node running on each machine. So typically we run Flume agent on almost all the nodes of our web server, and then and with tiers of aggregating nodes, as in combining them together, the data flows on its way to HDFS. Okay, so using these kind of mechanisms, you could create best effort delivery and end-to-end delivery while combining these source and sync together. All right, let's try to do something here. Let's try to create, let's try to create this. Let's try to create a Flume agent which will consume the data from a particular place. Okay, so there is a question. So Rohit's question is, can data flow? Very interesting question. Okay, so can data flow in reverse from HDFS to data source? No, it's a one way. Okay, in case you want it to flow in another direction, you have to connect it accordingly. Okay, you have to connect it accordingly. All right. Remember our USB power bank. In case of a power bank, sometimes we want to flow the charge into the power bank, and sometimes from the power bank. So we change the locations. There are two holes in that. Okay, it's exactly same mechanism. It's exactly same mechanism. All right, sounds good to you? All right, great. All right, so let's try to get the hands-on done on the Flume. All right, then if time permits, we will try a bit. Okay, let me download. Do we have it in HDFS? Do we have it in HDFS? It should be in HDFS. All right. So let me just go to this place. Okay. Did it work? No. So please note that it is in H3. All right. So let me just check our data folder. Okay. So we have FlumeConf here. No worries. All right. We'll just use this and copy this file to local. Hadoop. So let me check. Oh, good. So we'll say Hadoop fs minus ls. Okay. Fs minus ls conf. Good. Hadoop fs minus copy to local data flume conf flume dot properties. Okay. And let me just copy the full folder. All right. So we are okay. So the conf folder has been created. Good. Now, let me try to. Okay. All right. Now let's have a look at what is there inside this. Okay. I need to write some to-dos for myself. Okay. To do one is we need scoop and other is okay. And the third thing which we were trying just now is okay. Okay. Install. Do it have a nano? Good. All right. Now let me just have a look at what is there inside this Flume. You can see that what do we have here inside? So not this one. Delete this one. In the conf folder. In the conf folder, we have flume.properties. We say nano flume.properties. Okay. So you have this. Out of this, now let's go through this file a little bit. So as we talked earlier that Flume is made up of agents. These agents will run on all the nodes from where we want to gather the data. Now these agents, we need to define these agents. What do these agents do? So agents, first of all, we declare that agent has got this sources, these sinks, and this is the channel. Now we go into the details of each source. We say that source.r1.type is this, bind is this, port is this. What does it mean? Here we are saying r1.type is netcat. What is netcat? Netcat is a way to connect to any port and read data or write data to it. Okay, so here we are saying that the netcat will read data from localhost at this particular port. Okay, it will basically run a daemon which will open a port at this local host at this port, and then it will start listening there. You can dump the data at that port later on. Okay, I'll show you that. Now, next is we describe the sync type. We are saying sync type is HDFS and this is our location. So we'll just modify this because this is what we do not want. Okay, all right. Also, we will just change it a bit. We'll just give its path. What is our login name? Okay. All right, so this is the folder where we are going to run, and then we have the channel type. Now, channel, what's the point of channel? The channel could be something which saves in the disk. Channel could be something which can store 1,000 elements or 10,000 that we need to configure. We have to tell whether it's memory or disk or what is the capacity and how many transactions per second can it handle. Okay, so those kind of details we need to tell about the channels. Okay, now next is we tell uh, the we tell the sources that this is your channel, because source also need to know about this channel. Similarly, sync also need to know about this channel. So these these things we describe here. Next, the next step is, once we have described it, we run the Flume agent. Once we have described all of these details, then we run the Flume agent. Okay, we run the Flume agent saying Flume ng, and let's just try to put it here. So it, okay. By the way, this slash means that we have our command is spreading to multiple lines, not only single line. So here we are saying Flume ng agent is this and confile is this and conf folder is this. Okay, so we go in here. It says that a specified configuration file does not exist, which is right because we are inside the configuration file. All right, let's see if it works. All right, I think it has started the sync. Okay, let's open one more um let's say we have one more here, and we log into your folder. Okay, so this is one terminal. We are opening one more terminal. Why? Because we want to feed some data to our Flume. Okay, now Flume has started. Flume is listening on a port. Now, whosoever writes to this port, it will push that data to HDFS. Okay, and how do we write to a port? By saying NC. NC is that uh, general tool with which you can connect to any port running on TCP/IP. Okay, so here the port number is, okay, it says connection refused. Will it work? Oh, we have to log in into the same IP address. Okay, we have to log in into same IP address because it's running on localhost. Had we specified 000, it could have run on every host. Okay, so let me just open a console and SSH. We'll say SSH this, and we'll say H. What was that? This thing H3. It would be something else actually. Are we on the right node? Just give me a second. Let me kill it. If config. What is the port number? This is the IP address. I'll just run it on the IP address. Okay, this is the IP address. Okay, all I'm trying to do is log in onto the same machine there. But this is strange. Why I'm not able to log in onto the same machine? Okay, so I've logged in onto the same machine. Now here, let me start our Flume again. We are saying Flume ng means next generation, and agent and config is this, and then we are also mentioning the name of the agent because one Flume config file can contain multiple agents. Okay, so here we have to tell that which agents do we want to boot. Okay, so now while it is running there, let's try to connect to that host and try to write to it. So whosoever is giving out the data will write to it at this point. Okay, so are we doing the right thing? Is it correctly listening? Okay, now it's listening. Now at the parallelly, let's check what's going on in our home folder. Okay, did it create a folder called Flume something? Did it create that particular folder? So if I write data to it, it's actually would be going to the Flume agent. So I'm connected to the Flume agent right now. So we started a Flume agent, and Flume started listening to a port. Listening means waiting for a connection on that port. And now on this window, on this terminal window, I am connected to that particular port and talking to it. And while in the background, Flume is writing the data. You see, here Flume is writing data in this folder. Okay, so here Flume web data. Do you see that this folder got created? And as and when we are writing data here, you can also connect parallelly and write to this. Okay, so multiple people can connect to this, and then this data would be going here. Okay, and the moment I disconnect, okay, so now you can see. All right, so we were able to successfully create a Flume agent and write to it. Now you see, for every few seconds, it creates a new file. So web data, from Flume web data, you can create, you can load at various, I mean, you can load in Spark and other places. You can see that this is the data which we created. Okay, this is the data which we created. All right. So that's how the Flume works, and that's how it does the loading of the data. All right. Now, question from Haritha is that how do you? It's an interesting question if you think about it. So Flume agent doesn't stop; it just keep waiting for your data. The way you stop is by going to this, either killing the process or by pressing Control C. Okay, so so that's a very interesting question you asked. I'll explain to you why this question is so relevant. Most of the producer consumer, most of the producer consumer have this behavior that source, or let me say producer dash 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 and consumer. Okay, so although here we just killed the process, now in most of the cases these producer consumers keep infinitely running. If producer is not producing something, then consumer is waiting, and in case consumer is not able to consume at time, then producer is waiting. So they keep waiting for each other all the time. Okay, so they keep waiting for each other all the time. If this queue gets full, then producer waits. If queue gets empty, then consumer waits, right? Because queue will get empty when producer doesn't produce, and queue will get full when consumer is not able to consume. Okay, so these keep waiting infinitely, and if you have to test, if you have to test such kind of thing like a Flume agent, then you will question, then how do I test? Because there is no end to it. Because there is no end to it. Maybe if I kill the process, maybe my data is still lying in the pipe and it has not gone into the output, right? That's why we generally introduce the ideas like poison when we have to test the producer consumer. So producer generates a poison, and consumer knows that in case poison comes along, consumer has to stop waiting for data and exit. Okay, so that's where the idea of poison comes along. All right, have a look at how does Go implements poison. Go is a programming language from Google. So basically, it's a very important question if you think about it, that how do you test producer consumer? Because you started the process of producer consumer, now they're not stopping. Now should you kill them? If you kill them and then measure that whether whatever producer consumed did sorry, whatever producer produced, did it did it got consumed by the consumer? So if you have to test that kind of thing, it's fairly difficult scenario, and it's inevitable, and therefore you generally devise something called a poison. When you give the poison to producer, as soon as it sees the poison, puts the poison in the channel, and producer exits, and the poison goes to the consumer. As soon as it sees that okay, the poison has arrived, it exits. So the machinery gracefully shuts down when you put the poison. So that's how it is. Generally, that's how most of these producer consumer or kind of things work. All right. So that's pretty much about our scoop. So we will talk about few things. We will talk about scoop, Uzi, and we will also talk about Mahat and the project tomorrow. And we will also compare various NoSQL solutions tomorrow. Okay? All right. So tomorrow's class, be ready. We might extend it for maybe 10-15 minutes. Okay, so be ready for that. All right, thank you very much and have a good day. Bye bye. So, all right. So Rohit's question is, will we also cover Kafka? Kafka will be difficult to cover. Instead, what I can do for you is I'll just send you a video which covers Kafka and Spark in detail. Okay. All right. Bye bye. Have a good day.